In this problem, it's talking about a standardization experiment. So this is a titration, and we've got two solutions, an acidic tin to chloride solution and a potassium dichromate solution. So we're trying to determine what the concentration of the potassium dichromate solution is. But before we can perform the stoichiometry and solve for the concentration, we have to predict what the redox reaction is going to be in this case. And we do that by listing all of the entities that are present and then predicting what the strongest oxidizing agent and the strongest reducing agent are going to be. So if we go through and read the problem, the first solution that I have is tin 2 chloride. So for a tin 2 chloride solution, I'm going to have tin 2 ions, and I'm going to have chloride ions. The second solution is a potassium dichromate. So we'll have potassium ions present, and we'll have dichromate ions. As well, in addition to our ions that we have in solution, because it's an aqueous solution, we know that there is water present. So we've got H2O liquid. And then going back to the problem, right at the beginning here, it told us that this was an acidic tin 2 chloride solution. So if this is an acidic solution, that means there's hydrogen ions present. So I do have to include that on my list of entities present. Now we'll go through and identify, is it an OA or is it an RA? I like to list the OAs across the top and RAs across the bottom just to keep myself organized. In some cases, the entity could act as both an OA or an RA. So tin 2 plus, for example, this could be reduced to become solid tin, or it could be oxidized to become tin 4 plus. So this can act as an OA as well as an RA. Chloride ions are an RA. Potassium ions is an OA. Dichromate on its own isn't a very effective oxidizing agent, but if there's hydrogen ions present, then it actually can be a pretty strong oxidizing agent. So these two as a pair are an OA. Water can be oxidized or reduced, so this is going to be an OA as well as an RA. So now we got to go to our data book and take a look at that redox table. Starting from the top left corner, where the strongest oxidizing agents are, we're going to scroll down and see which of these OAs that we've listed here appears first. So beginning in the top left corner with F2 being the strongest oxidizing agent on this um, reduction half reaction table, we're going to scroll down and see which of the OAs we see appear first. So starting with the F2, scroll down the table, and the first one that we come across is dichromate and hydrogen. So those two as a pair are going to be our strongest oxidizing agent. To find the strongest reducing agent, we start at the bottom right corner and work our way up. So lithium being the strongest reducing agent on this table. So as we start scrolling up, we're looking for the first SRA, and we see it here, tin 2 plus. That's the first one that we see appear. So it is our strongest reducing agent. Now remember that your strongest oxidizing agent is reduced. I always remember this with the acronym SOR. Okay, so we'll start by writing out our reduction reaction. Strongest oxidizing agent is reduced. And this half reaction you can just obtain right from your data book. We've got a dichromate, and it's going to react with 14 hydrogens. There's a total gain of 6 electrons, and we're going to produce 2 chromium 3 ions as well as 7 water. For our oxidation reaction, we have tin 2 plus being oxidized, so I've got tin 2 plus. Oxidation, we're losing electrons, so we're showing them on the product side. We're going to lose 2 electrons to become tin 4 plus. Now remember that the total electrons gained has to equal the total electrons lost in this reaction. So in order for the electrons to be balanced, I have to multiply my second reaction. So this is my strongest reducing agent, which is oxidized. This half reaction has to be multiplied by 3 in order to balance those electrons. When we multiply by 3, we get 6 and 6 and the electrons will cancel. I like to keep these arrows lined up because it helps me when I'm writing out the overall reaction to see what's on the reactant side, what's on the product side. So what we're left with is a dichromate, 14 hydrogen. The 6 electrons will cancel. When I multiply this by 3, it's going to give me 6. So these guys are going to cancel out. And then I also have 3 tin 2 plus. On my product side, I've got 2 chromium 3s, 7 waters. My electrons canceled. Don't forget we have to multiply everything in this half reaction by 3, so that would give me 3 tin 4 plus. Now I can use this reaction for the next step, which is the stoichiometry to solve for the unknown concentration.